Okay, last time I proved Noether's theorem, which is a statement that if you have a continuous global symmetry, then it implies a conserved current. So, continuous global symmetry that implies a conserved current. That is, you will have a quantity J mu whose when you take the 4 divergence, that will give you 0. Okay. And this you saw that further implies that you can construct a charge q, which is obtained by integrating over all space the J mu J 0, okay, and which for which dq over dt is 0. Okay, so the q is a conserved charge. So each every global symmetry that your theory would have, that would lead to a conserved current and a corresponding charge. Okay. And I also gave some examples of how you can destroy certain symmetries by putting some terms. Okay, maybe I think I will do this explicitly, so that we have at least one instance, one example where we know how to spoil things also. Okay, and I was I think referring to this one. So if you have, let me go to the next page. So let's take this action, which is a functional of field phi. So I am looking at Klein-Gordon theory. Okay. Now, remember that it is only the field over which you have control. So, if S is the functional of phi and it takes different values depending on what field configuration you give to it. Okay, so, if you change the field configuration, the value of S would change. You do not have any control over x, you cannot choose to do something to x. Right? It's an integration variable. The only thing you have access to is the phi. Okay. And I said that I want to choose a different theory, not the Klein-Gordon theory, with a spoiled symmetry, and I said I will take I will keep all this the same, but the second term I would change. So, I put an explicit x square here. Okay. Now, let us see how the symmetry is spoiled. So, you had you know that this theory has translation symmetry, meaning if I take the field phi of x and transform it to a phi tilde of x, which is related to phi of x by this translation, okay, meaning the field at point x in the transformed field is related to the field original field with the arguments translated. Okay, so, that is the field transformation that we have. And if I now, okay, just to remind you, in this case we had S of phi tilde is equal to S of phi, okay, because the time and space translations versus symmetry, and let us look at this one now. So, if I calculate S of phi tilde, you will get d4x del mu. Maybe I should just give the answer, because I think we have done already these kind of manipulations before. So, I will just give you the answer. So, del mu phi of x. So, I have put in this expression replaced phi by phi tilde. So, you will have in this expression phi of x plus a, and then I change the dummy variables, the variable x, so that I get phi of x, okay, and then you get del mu phi of x This you will be able to easily do. I hope I have not made any mistake in this. M square A x phi of x. Okay. You should not do anything to this. Remember, all you can do is change the field by phi tilde and then make this substitution, but you cannot do anything to x. You should not start putting x, you should not change this to x plus a or something like this. You should not do. Only fields you can transform. And once you do that and change the variables back to x, you would get this. Okay. And this is clearly not equal to s of phi. Okay. If the change was a total derivative, then we could have concluded that s of phi tilde is s of phi, because the total derivative you can ignore. Okay. Because on the boundary you can say the fields vanish, but this is not the case here. So, you see that I have spoiled the symmetry of translation. You should check whether we have also spoiled or not spoiled the Lorentz symmetry. So, you should check whether this is still a symmetry or not for this action. Okay, please do this part. Okay, so good. So, let us now apply Noether's theorem to Klein-Gordon theory. Okay, that is what we want to do. So, we want to find the conserved current, but before we find the conserved current, we should ask which symmetry we are talking about. Okay, so, let us list down the symmetries which we know already about this theory. Okay, and see whether that symmetry would lead to a conserved charge or not. So, you know time translations. That is a symmetry. Then we know space translations. They are symmetries. We have already done this before. We already know that boost is a symmetry. We know that rotations are symmetry. Okay, and actually, yeah, let me go further. So, and then you know time reversal is a symmetry, and then you know space reversal is symmetry of Klein-Gordon theory. We also saw that phi of x going to phi tilde of x, which is equal to minus phi of x, that is also a symmetry. Okay. And maybe there are more symmetries which we have not talked about. Maybe there are more to be discovered, which we have not discussed here. So, by more symmetries, I mean more symmetries of Klein-Gordon theory, because that is the theory I am looking at. Different theories will have different kinds of symmetries in them. It is not necessary that the symmetries which you have in this theory will be present in another theory that you can write. Okay. Okay, so, let us look at these symmetries. So, time translation, let us see, is it let us ask whether it is a global continuous symmetry, whether all the symmetries that I have listed are they global continuous, and whether they will lead to a conserved charge. So, time translation, yes, it is a global continuous symmetry. So, it will lead to a conserved current of its own. Space translation, so these are three global continuous symmetries. they would lead to 3 conserved charges, okay, and usually we call them momentum, okay, and the charge corresponding to time translation is called energy or the Hamiltonian. Okay. Now, boost is also a continuous global symmetry. So, that would also lead to 3 conserved currents and correspondingly 3 charges. Rotation, of course, continuous global symmetry, that would lead to, of course, conserved charges. Time reversal, is it a global continuous symmetry? No, it is not, because this is phi of x, phi tilde of x is equal to phi tilde of Tx is equal to phi of minus Tx. So, clearly there is no continuous parameter that parameterizes this transformation. Okay. So, it is not a global continuous symmetry, it is a discrete symmetry. So, you do not expect a conserved charge for this. Similarly, for space reversal, again there is no parameter which parameterizes this one, no continuous parameter. So, it is a discrete symmetry, and again you do not expect any conserved charge. This transformation, of course, there is no continuous parameter. So, this is also discrete symmetry. So, this also does not lead to, and if you could find other continuous symmetries which are present in the Klein-Gordon theory, you would have corresponding currents and charges. Okay, but we will only talk about these ones in our discussions. Okay. Okay. So, till now our discussion was in the context of when we were talking about Noether's theorem, it was general, but now we want to write an explicit expression for conserved current. Okay. See, earlier we just said that we will have this kind of expression. Okay, and we can read off as the coefficient of epsilon what is del mu j mu. Maybe I should go back and show you. So, you see here, if you did a transformation phi going to phi prime, where phi prime, remember, was not a symmetry transformation, okay, because it was phi prime was related to phi by this expression, where epsilon is x dependent, and only when epsilon depends on only when epsilon is a constant, this was a symmetry. Okay. So, for this transformation we saw that we could, based on general arguments, we could say that the change in the value of the action would be this much at order epsilon, and then we can read off del mu j mu if you could express it like this. But now what I am going to do is give you an explicit expression in a special class of theories, and that special class is the following. Where action is this. So, you have Lagrangian density here, and you have some fields phi I, and Lagrangian density depends on first derivatives and maybe second derivatives and maybe on higher derivatives. Okay. So, that is the general action that you could construct, where there are several fields labeled by I, but the restriction I am going to put is I will not include all these higher terms. So, my action would be just containing the fields and the first derivatives. Okay, that is the class to which I want to restrict to, and all the known interactions obey this, fall into this category. Okay. So, all known interactions in nature have action of this form. Okay, whether you are looking at electroweak symmetry, strong interactions, whatever you are looking at, they all will always have first derivatives. They don't have higher derivatives. Okay. Now, when we are looking at a symmetry, the action S phi of tilde is going to be the same as S of phi, and remember, in writing this we do not use equations of motion. This has to be true for any generic field configuration. So, whatever field configuration phi you take, and if you do a symmetry transformation to phi tilde, this should hold without using equations of motion. That is important. Okay. But for this to hold true, you do not need that the Lagrangian density should remain unchanged. So, even when Lagrangian density goes to it transforms to Lagrangian density plus epsilon times some total derivative term, that would still leave the action unchanged. Okay, I am here, epsilon is constant, and I am here thinking of an infinitesimal transformation. That is why you see an epsilon here. Okay, this should be clear, because if you put such a term in the action and do the integral d4x, this one you can ignore. Okay, because this integral del mu, integral d4x del mu k mu, okay, that is a volume integral over 4 volume. You can write it as integral d sigma mu k mu. Okay. So, what we have done is we have turned a volume integral into a surface integral. Okay. This is something familiar to you, and here it is boundary in space time, and because we are going to assume that the fields vanish at the boundary, this term can be ignored. Okay. So, this can be dropped. So, a total derivative change in the Lagrangian density is fine. Okay. Maybe here I should write. So, sigma is the boundary, okay, and d sigma mu is the boundary surface term, boundary element. And because I am assuming all the fields and the derivatives to vanish at the boundary, it will give you a vanishing contribution. Okay. So, that is allowed, of course, but it may happen that in certain cases the Lagrangian density does not change at all. So, the k mu is absent in some cases. So, it may happen that Lagrangian density as a function of phi, remember Lagrangian density is a function, not a functional, is as a function of phi tilde is same as this, and the k mu is 0, there is no k mu. Okay. And typically it will happen when you have internal symmetry, okay, because internal symmetry is not going to touch space time points, and if it does not involve space time, then it cannot generate a space time derivative. Let me make this more concrete by giving an example. So, so for internal symmetry, okay, if you do the transformation, then that is k mu will be 0. Okay. So, you can see it from this example that if you take a charge scalar field, okay, let me not use the word charge, if I use complex scalar field. So, you have del mu phi dagger x, del mu phi x. So, now phi is complex, minus half m square. Okay. it's just complex. Even though I am writing dagger, it's really star. So, this one has a symmetry that if you take phi to phi tilde, which is e to the I alpha, where alpha is a constant, times phi of x, then because each term has a phi star phi, this will have e to the I alpha and the phi star would have e to the minus I alpha. So, they will cancel and leave behind the same thing. So, you see, not only the action remains unchanged, even the Lagrangian density remains unchanged, because there is no derivative term generated, and because it is acting on internal symmetry. Okay. So, here by internal symmetry I mean the symmetry is mixing what is phi real and phi r, phi real and phi imaginary. The real and imaginary parts are being mixed into each other by this phase. Okay, and that is why it's called an internal symmetry. Okay, so that is fine. Let's see. Now I want to write down an explicit expression for J mu. That is the goal in a general theory. Maybe I should go to another page probably. Okay, let's see. Okay, so let's take Lagrangian density, which is a function of the fields and their first derivatives. Okay. So, Lagrangian density is a function because if you specify the value of field and the first derivatives at a point, you get a number. Okay, a function is that is a quantity which gives you a number if you specify some variables. For example, f of x is x square. So, if you choose a value of x, you get a number here. Okay. So, similarly here, if you choose a value of given a field, if you choose a value of x, then that is the variable you have, and these are remaining variables, and that gives you a number for the Lagrangian density. So, it is a function. Now, I look at the symmetry transformation. This. So, this is specified, some theory is specified to you, and let us allow for multiple fields. Okay. And then also I specify a symmetry that this theory has, and I say okay. So, that is an infinitesimal symmetry. If you tell me what psi of x is, then the symmetry is completely specified, okay, by this information. But let us keep it general. We do not specialize to any particular symmetry. We say this is the symmetry, okay. And then clearly, if I am looking at the derivative terms which are going to appear in the Lagrangian density, I can already write down the expression for it. So, it will be just del mu of phi I of x plus epsilon. Epsilon is constant because we are looking at global continuous symmetries. So, the derivative acts only on this piece. Okay. Now, I will do a Taylor series expansion. Taylor expansion. So, I should be calculating the Lagrangian density at phi tilde and del mu phi tilde. This is the transformed Lagrangian density as a function of transformed fields, and this would be to order epsilon to the 0, it should remain unchanged because of this and this. If I put epsilon equal to 0, the phi tilde and del mu phi tilde, they are exactly the same. So, I expect it to be the same, original Lagrangian density, and then corrections of order epsilon. Okay. And what are those? So, because it is a function of these variables, I will take a derivative with respect to these variables. So, del L over del phi times the change in phi, and that is epsilon times psi, okay, plus del L over this thing, del of del mu phi I, and then you get this change. So, epsilon del mu psi I, and of course, order epsilon square terms which I omit. And as I said that in general, this would be the Lagrangian density can change by a total derivative if you have a symmetry. So, in general I would be able to write it as epsilon times del mu k mu for some k mu. Okay. Okay. Now, remember here we have talked about a symmetry, but the way we have formulated Noether's theorem, we want to promote epsilon to continuous local symmetry, meaning we want to take epsilon and make it x dependent, okay, and then read off the total derivative term that gets generated. So, that is what I will do. So, make epsilon a function of x. Okay. So, if I do so, then I am not looking at symmetry transformation, but I am looking at a different transformation, which is, let me write here, phi prime of x. Okay, I distinguish by the symmetry transformation with constant epsilon with this transformation by putting a prime here, plus epsilon x psi of x. That is psi I keep the same. So, that when I take epsilon to become a constant, I collapse onto a symmetry transformation. And similarly, del mu phi I prime okay. So, let us now I think I need to go to the next page, which is not the best thing to do. Okay, I think we can remember this. So, we just need to remember this, and I am going to the next page. So, let us see what is L of phi prime. So, L of, let me write here. So, we have L of phi prime is, just a second, there is someone at the door. Okay, so sorry for the disturbance. What was it? Okay. So, L of phi prime is, what happened? Something changed. Yeah, is going to be L of phi plus those order epsilon terms. Okay, so I am going to write now L of phi prime minus L. What is the difference? So, L of and phi prime of x this difference is equal to that is what you have del L over del phi I times the change, and the change is epsilon times psi I of x, right, and then the change due to the derivative and then the change in the del mu phi, that is del mu of epsilon times psi. Okay, that is just the Taylor series expansion, plus of course higher order terms are there. Now, I can do a simple thing. This term is fine. Let me write it anyway. No, it's boring to write so many times. So let's look at this piece. This one I will write as, I will just put the derivative here. So you generate a term epsilon of x and the derivative x on this one. So you get epsilon of x, okay, del L over del mu phi I times del mu psi. Okay, and then there is another term in which the derivative x on the epsilon I think I should have. Okay, there is no need to. Let me just write the answer. That's fairly simple, so you can do it. So all you have to do is let me write the answer and then we can understand. Yeah. So you have epsilon of unnecessary deleted. It's okay. Let's see. Okay, let me write it anyway. I should not change my plans in between. Plus, so epsilon del L over del mu phi I times epsilon of x and del mu psi I of x plus phi I and psi I of x and del mu epsilon of x. Okay, that is good. Now let's go back and check here. When we were looking at the symmetry transformation, okay, then we had this piece epsilon del mu k mu, and what was k mu? K mu was just the coefficient of epsilon from these two terms, which is del L over del phi times psi and del L over del mu phi times del mu psi. Okay, and that's the piece which you see here. If you pull out this epsilon outside, okay, then this is exactly what you saw for k mu in that previous page. Not k mu, del mu k mu, sorry. Okay, we should not, I made a mistake, I said k mu, but you have del mu k mu. Okay. So, these two terms I have taken care of, and now we have this last piece. Now, what I will do is I will transfer the derivative from here to this one, which will give you a minus sign. So, minus del L over del mu phi I, okay, and you get a del mu plus the derivative with all these terms together. del mu epsilon of x over del mu phi I. Okay, let's check whether everything is fine. So let's do this one. So when del mu when del mu acts on epsilon, so you get del mu epsilon times this piece, which is this term, and then when del mu acts on the remaining two, you get epsilon outside. So which means I have missed epsilon here. Okay, so you get epsilon of x times del mu of this entire thing, and these two cancel. Okay, and these first two terms anyway have used up in writing del mu k mu. Okay, so these two together correctly give me the last term in this equation, and the first two are already k mu. So everything is right here. And the reason I have arranged it this way, because you see this is a del mu total derivative term here. Okay, and then when I look at the action under this transformation, which is not a symmetry transformation, okay, this total derivative term I will be able to put to 0. I can ignore this term. So what we have now is s of phi I prime minus s of phi I is equal to integral d4 x, okay, epsilon of x. I am just substituting the Lagrangian density, del mu. So this also has a del mu and this also has a del mu. Okay, del mu acting on the whole thing, and you have epsilon x here. So I can write it as del mu k mu minus times psi I of x, where psi x is the change, okay, due to the symmetry transformation. Okay, and this I am ignoring the boundary term, Okay, so now we just use our proof of Noether's theorem, that we read off J mu by looking at this thing. The coefficient of epsilon x was del mu J mu, so we get a conserved current J mu is equal to k mu, or maybe I can write this one first. Psi I of x plus k mu. Okay. So that's our expression for the conserved current in the case of this special class of actions where only the first derivatives are present. Okay, and I have made no assumptions about this. So the fields are general; they are not necessarily scalar fields. Okay, and this psi I. I have not made any assumptions about what psi I can be. I am not using scalar. So there are n number of fields, and they can be whatever they want. And this is a generic symmetry transformation. The k, the capital K, is the one which is the total derivative term which is generated when you look at the symmetry transformation. Okay, so you should contrast this one. This is different. That is not due to symmetry transformation, because epsilon is x dependent. Anyhow, we have found the conserved current J mu is this much, and that is what we wanted to know. And now with this you can construct the conserved charge. Okay, so let me write here itself. So all you have to do is q is integral d cube x j 0. Okay, that's the conserved charge, and dq over dt will be 0. Okay, good. So we will continue our discussion further on Noether's theorem, and we'll talk about some examples. We'll talk about space time translations. We'll talk about Lorentz transformations and all these things in the later videos. Okay.